Welcome everyone to a tropical Tuesday. We are working with our special triangles. So we want to get this triangle into our page and this triangle into our page so that we can fill in the values of sine and cosine for the various angles. So I'm going to move myself over here where I'm less of a bother. And we see over here, this is 45 degrees. So the way we find that sine and cosine is we're going to take a look from here. This is looking from 45 degrees. My opposite over hypotenuse would be sine. Sine is opposite over hypotenuse, so 1 over root 2. And cosine is the same, adjacent over hypotenuse, 1 over root 2. So along the unit circle, this would be the point 1 over root 2 and 1 over root 2. And then, because we have one whole quadrant labeled now, and we labeled these points here with the 30, 60, 90 triangle, so you can work those out as well with this triangle. What we can do now is take these different measures and extend them into the other quadrants. So go ahead and label your angles. This is 180 minus 60 degrees, so this is 120. This one is 135. 180 minus, oops, I just put 134. 180 minus 45 degrees. It's 135. And this one is this is 180 less 30 degrees, so this is 150. Now the values for sine and cosine here are going to be the same as these values, except all of the x values are going to be negative. That's the only difference. So here, 60 degrees is the related acute angle for 120 degrees, because here, this angle here, 60 degrees, is going to be related to 180 minus 60 there. So we can pull our values for sine and cosine for 120 from over here, 60, except it's going to be negative 1/2 and then root 3 over 2. And you can work out the rest of them just by pulling these over. 1 over root 2, but negative, and 1 over root 2 positive. And then over here, root 3 over 2, but negative, and then 1/2. And remember, yesterday we learned and this of course the point negative 1, 0. Yesterday we learned a trick with our hands to remember the different sine and cosine for the various special angles, 60 degrees, 45 degrees, 30 degrees. So that's something that you can also use to fill this in as well, counting your fingers and take the square root, put it over 2 on either side for sine and cosine. And then down here in the bottom half, we're going to do the same thing, just pulling over our related acute angles. In this case, the related acute angle 30 degrees is related to 180 plus 30 degrees. So that's 210. And it will have the same values of sine and cosine as this, but both will be negative because it's down here in the third quadrant. So that's going to be negative root 3 over 2 and negative 1/2. And if we look over here, if you just take a look, this is negative 1/2, and this is the point 0, negative 1. So you can make these types of marks for yourself and just see those relationships. Let's get rid of that. Okay. And then this one here is negative 1 over root 2. This one is negative 1 over root 2. And this one here is the same as this, but flipped. So negative 1/2 is negative 1/2 in the x, and negative root 3 over 2 in the y. And these are the angles 210, 225, and this one is 240. That's 180 plus 60 degrees is 240 here. And then this is the angle 270. This is the angle 180, of course. I didn't get that one labeled, but you can label it. And then these ones, this is 270 plus 30, but actually we think of that as 300 less 60, so this is 300 here. And it's going to have the same sine and cosine as the angle 60 degrees, except here, cosine will be positive and sine will be negative. So we had 1/2 and 3/4 and root 3 over 2 there. So we're going to have 1/2 and negative root 3 over 2 here. This one is 315. And it has 1 over root 2, negative 1 over root 2 as its sine and cosine. And then this one is 330. And it's negative root 3. Oh, no, it's not. It's positive root 3 over 2. And negative 1/2. Okay, so now we have all of the special angles labeled onto our unit circle, and we can use this to plot these values for sine and cosine on the opposite page. So you may have to do some flipping back and forth to get this to work nice, but we'll do each one here. What's that? Oh, sure. So there it is there. Which quadrant do you need? Yeah, so let's, rather than me show you what the values are, show you how to get them. Here's 30 degrees, 45 degrees, 60 degrees. We can find these values for sine and cosine, and they will be the location of these points around the circle. That's how I had that magic point go around the circle there. I just put in cosine A and sine A. It moves around very nicely. And then I use my cast rule. So my cast rule is telling me which values of sine and cosine are positive and negative in which quadrant. So cosine is positive down here. Those are my x values. All of them are positive over here, so that's both values are positive. Sine is positive here. Those are my y values. And neither sine nor cosine, only tangent is positive down here. So that's my CAST or cast rule. And that's how you can just apply the proper plus and minuses to the different points. But also we're pretty familiar with the coordinate plane now. We're probably not surprised that our x values are positive and our y values are negative over here for these angles.
So it's 330 on the bottom right there. What's that value right there?
Root 3 over 2. Root 3 over 2. Yeah. And we get that one from this triangle over here. You see, if I draw that triangle on, it would look like this. It would go along here and come down. There's my 30-degree angle here, my 60-degree angle there. This is 1, this is 2, this is root 3. So this would be root 3 this way over 2, and this would be 1/2 this way. You'll notice if I bring this over in a straight line, it's exactly half of the distance from the center of the circle to the circumference to the circle. So that's negative 1/2 in the y. So that's how you can get those points. Now let's go ahead and use that to graph our sinusoidal functions. And we're going to be using the different ones here. You're going to create them for a few angles. And I've highlighted all the special angles here, so we can put those in. This one, we're going to do that one for 30 degrees. So here is 90 degrees over here. We're going to have 30 degrees there. So draw on your arm for 30 degrees. So you're going to draw an angle that goes up 30 degrees there, create that triangle, and label the point root 3 over 2 and 1/2. Okay, so there's my values for sine and cosine. Okay, I'll zoom in so you can see that a little better. I should have zoomed in to draw it a little better, but there you go. So there's my 30-degree angle. You can put on 30 degrees here. And then here's our value for sine. So you can go ahead and label your axes here. I'm going to put number 1 up here. This is my 1 in the y. This is my negative 1 in the y. And now I'm going to put my values for, let's call this f of x. So you're going to label this f of x equals sine of x. We're going to graph that one up here. And down here, you're going to graph f of x. Let's use another color. Just make it beautiful. G of x, it's a different function, equals cosine of x. All right. So let's graph sine first, and then we'll graph cosine. So here, to graph sine, I first want to know, well, what's my sine at 0? So if I forget, I can go ahead and look at my unit circle down here, and I see, oh, right, the value of sine at 0 is 0. Sorry, it's 0 degrees. Sine 0 is 0. My calculator also tells me the same. And then, so I plot that there. All right. And then my next point over here at 30 degrees is up there at a half already. And then here at 60 degrees, what is it at 60 degrees? I can even put on 45 degrees here, which would be right in between 60 and 30. And so if I'm not sure, well, what is 1 over root 2? You have to punch these things on your calculator, and it will tell you. 1 divided by the square root of 2. Oops. There. 1 divided by the square root of 2. There. And then it is equals to 0.7. 0.70, blah, blah, blah. So that's how you would punch that on your calculator. 1 divided by the square root of 2. You don't need to do 1 divided by 1 divided by. Yeah. So anyway, that is for 45 degrees. So go ahead and put that on. If this is 0.5 and this is 0.75, 45 degrees is going to be just a little bit lower here, about right there. Okay. And then at 60 degrees here, well, that's root 3 over 2. So let's go ahead and punch that on our calculators. So then we will have here the square root of, just clear all that, the square root of 3 divided by 2 is going to be 0.8 something, is 0.866. So it's closer to 0.9 than it is to 0.8. So it's already very close to 1, very close to the maximum value of sine here at 60 degrees. So there is 0.75. Here would be 0.8. 0.9 might be up there. So we'll put it about right there for this one. And then the value of sine at 90 degrees, well, that's 1. That's the maximum value of sine. And then this function is going to be symmetrical around this line all the way to 180. So now I can go ahead down here and look over here and see, oh yeah, it went up to 0.866, went up to 1, and now it's down to 0.866. This is 0.7, and then it goes to 0.5, and then back to 0 by 180. So I can go ahead and plot all of those points over here as well. So this is 120 degrees, and it should be level with that point. And then here is 40, this is 135 degrees, so it's going to be level with that point over there. That's 0.7. And then this one here is, again, right at 1/2 for 150 degrees. And then back to 0 degrees down here at 180. Okay, so now I can start to see this curve happening, and it's going to repeat over here on this corner as well, but just reflected through the x-axis. It's going to be all the negative values. And now let's put on for our unit circle here, let's get this angle 135. So go ahead and draw this one on, just to remind yourself the connection between the unit circle and this point. And this point here would be negative 1 over root 2, comma 1 over root 2. And that's the angle 135 degrees. And we can get this, of course, from our unit circle over there. So go ahead and get that on. And that's happening over here. You can even label this point here as in the x, it's 135, and in the y, it's 1 over root 2. So this is the point 135, 1 over root 2. That's that point right there. You could label this point as well if you wanted, 30 degrees and 1/2. So that's the point 30 and 1/2 right there. And then we can connect those to the unit circle. Now let's do the other side. So it's going to be a reflection. So I know that here it's going to be there. Here it is going to be about there. And here it's about there. Okay. Let's verify this point with the unit circle. That's 270 less 30 degrees. That's 240 degrees. So 240 degrees, you draw it on here. It's an angle about like that. This is 240. And this would have the point here in the x, it's negative 1/2. And in the y, it's negative root 3 over 2. And this is the value here, negative root 3 over 2. Notice that it's just a reflection of this point over here, root 3 over 2. Okay. And then the last thing that we're going to do is finish out the last 90 degrees. It's going to be a reflection through this line, through 270. So this point would reflect over here, because that would be the case when we just extend this angle a little bit more over here. The value of sine there is still going to be in the negatives, the output there, the y. And yeah, it's going to be the same as this. It's just going to be reflected across the x-axis there. This point here is going to be, again, 1/2, and then we're back to 0. And so now it's time to draw a smooth curve through these points. Try not to go over 1 like I did. There. And that's going to repeat every 360 degrees. We're going to have the same pattern. And here's our sine wave. Notice that sine starts at 0, 0. That's its y-intercept, is the 0. And then it rises before it falls. And also we saw that in the ambiguous case of the sine law, you could have two different solutions for a different value sine. And that's, you see that kind of there. Like if your sine is root 3 over 2, then it could be either one of those points. Dave? How I'm finding the points? So you could punch them on a calculator, and you could say, what's the value of sine at 90 degrees? So sine 90, what is that? Punch it on your calculator. Sine 90? 1. So that's up there at 1. And then if we punch 120, well, that'll be root 3 over 2. That's here. And your calculator will probably tell you 0.866. Now, Dave, we're using the unit circle to get those points. So here's the unit circle at 135. So here is my x value here, the angle. The y value here is the value of sine for this angle, because sine is going to be related to the height of this, this part of the triangle there, and the height there is 1 over root 2. So when we had 135 as our x value, our y output was 1 over root 2 for the function f of x is equal to sine x. Cosine is going to be very similar, and we can use the same drawings. Oh, over here you could draw 360 degrees. Use this one for 360. This is the angle 360. And here you have the point 1, 0. It's already on there for you. So that gives us the value of sine as 0. And there it is right there. Dave, does that answer your question? Kind of. Okay. Our input is the angle. As we rotate that arm around the unit circle, our output for this case is sine. And sine will be the value of the y of that circle. If I show you again my terrifying trigonometry graph in Desmos, and I show you this point here, let's open this one. Okay, we'll turn off of the Ferris wheel itself. Here's the point cosine of A, sine of A. Okay, so you'll notice as the angle goes towards 0, it follows the circle perfectly, and it does that because I have the value of cosine for the angle as the x-coordinate of that point, and the sine of that angle as the y value of that point. Okay? And the reason it does that is because its radius is 1, so all of these are like some number over the hypotenuse. Well, the hypotenuse is 1 in this case, and that's why it corresponds exactly to the unit circle. So let's now graph our cosine curve. So in this case, we can use the same pictures here, and we can use our unit circle over here to do that. Our first input is 0 degrees. That's where we're going to start the curve. And our value for cosine is given by the x-coordinate, the x value here. So this is adjacent over hypotenuse. In this case, the adjacent is the hypotenuse. I haven't opened up the triangle at all yet. So this side that like it's cast down here, when it's 30 degrees, you see it's not as long as the radius. But when it's down here, the radius is the adjacent. And so you're saying divide the adjacent by the radius. Well, that's 1 divided by 1 is 1. So that's why cosine starts at 1. So you can go ahead and put that value on. You can draw it in a different color if you so choose. It's going to start at 1 up here. And that's this, we get that value from, well, we have it over here on 360 is the same as 0 degrees. 360 is the same as 0 degrees. The value there for cosine is 1. And then it's going to go down to 30 degrees to root 3 over 2. There's our cosine. So put root 3 over 2 on. It's a little closer to 9 than it is to, sorry, to 0.9 than it is to 0.8. So put it there. And then at 45 degrees, it's going to be 1 over root 2. So we know that's a little bit less than 0. It's a little bit more than 0.7. So we can put it about there. And then here at 60 degrees, the value of cosine is 1/2. If you look from over here, from this corner, if you make this your angle of interest, here's your adjacent side, here is your hypotenuse. So the value of cosine 60 is 1/2. And your calculator will tell you the same thing. You could just plug and chug these on the calculator, but I want you to imagine and visualize the unit circle. And visualize how the unit circle, and we rotate that point around, how that input of an angle can change sine and cosine and create these wave-like patterns in sine and cosine. And then at 90 degrees, it's 0. Value of cosine at 90 degrees is 0. So cosine is going to start with the top end of its curve and come down to 90, and then continue on down. It's going to be at a 1/2 here. And let's check in with our unit circle here for 135. For 135, here is the value of cosine. It's negative 1 over root 2 for angle 135. So here's 90, 120, 150, so 135 right in the middle. And there it is down about there. So there is our point 135, negative 1 over root 2. And then this one is over here, negative root 3 over 2. And then at 180, if you do the cosine of 180 degrees, that's where you get negative 1. So this curve continues on down here and levels off, has slope 0 there, it's flat, and then it continues in a mirror-like pattern over here, like so. Not needing the unit circle anymore, just seeing that we have some symmetry, so we can graph using our symmetry all the way to there. And then we'll notice that this whole function is symmetrical around 180 degrees. We're going to have the same thing going on that side as we do around that side. So go ahead and put those points on. This one's going to be at 1/2. So what is that angle? This is 270 plus 30. That's 310 degrees. So if you're confused or you want to just check your work, go down and check your 300 degrees. Sorry, not 310, 300 degrees. 270 plus 30 is 300. Thank you very much. And our value of cosine there is 1/2. So great, that's 1/2. And there it is, 1/2. Okay, that fits our pattern. This one is going to be just there, 0.7. This one here, and this one here. So graph it. And so there we have our graphs for sine and cosine built using the unit circle. Okay. So you can also fill in this table here. The maximum value for the sine function is 1. Its minimum value, negative 1. Its y-intercept, well, you can go ahead and find its y-intercept there. Maximum value here, minimum value here. Maximum value of cosine is there, but it's also there. The minimum value there. Okay, and yeah, fill in these tables. When we look at the amplitude and the equation of the axis, here, remind me, what does amplitude mean? Dave? Yeah, like how big is the range? So really the amplitude is half of the size of the range, because the amplitude is the distance from that midline axis to one of the maximum or one of the minimum is our amplitude. So in this case, the amplitude is what for sine and cosine? Here's the axis of symmetry, the horizontal axis. Yeah, it's just 1. This is 1 higher than that. So that's amplitude 1. So it couldn't be simpler. And then the equation of the axis is the same in both cases. What's the equation of the axis here? Remember, it's an equation. Y equals 0. Yeah. Okay. So we can see the amplitude here. You could draw that on like this. Amplitude equals 1. And then you can even draw on just your equation of the axis there. Yes, I know it's already drawn for you, but it helps to draw it. Good learning. Axis. The axis is y is equal to 0. Just the x-axis is our axis there. And then, what's the period of these functions? Can you give me a definition of period? It's the amount of time or the amount of x value that you need to go through one complete cycle. So if the periodic function goes up, comes down, goes up again, then we would just take a look at where do we get to the same point going in the same direction on both sides of the curve. And what's the distance there? So what's the period for these functions? 360, yeah. So we're looking at only one cycle here in our graphs. If you took this, copied it, and pasted it over there, it would continue on forever, going up and down, up and down. So our period here is 360 for both of them. And then domain and range. So x's of the reals. Are there any restrictions on x for our domain? No. What's the restrictions on y? Y is also of the reals, meaning that we can get numbers that are non-integers. We can get all of those weird fractional numbers and square rooty numbers.
-1 is less than or equal to y, which is less than or equal to 1.
Yeah, -1 less than or equal to y, which is less than or equal to 1. Good. And then you can close that bracket. So just a brief review on this is how we can write domain and range. I should have a colon there as well. And now this is a statement saying y always falls between -1 and 1. Okay. And if you take a look at my funky trigonometric graphs in here, where I have my sine waves. Oh, they're not fault. I don't have the. Oh, I do have them synced. Yeah. So that's there's a sine wave. And how do I get it to only show me part of it? Well, you can restrict the range in Desmos with the same types of equations, or the same types of inequalities here. So you'll notice that I've told it to graph me x, where x is always bigger than 0, but less than 4.5, and it only shows me this section of the curve there. So you can do the same thing in Desmos to play around. Okay, and so that's this idea. Now, let's carry on with transformations of sinusoidal functions. So we were thinking yesterday about a bike tire that picks up a rock as it's riding along, and we wanted a function that would model the height of the rock. We could use either a sine or a cosine curve to model that, because sine and cosine curves are just horizontal translations of one another. If you go back to your graph here, you'll notice that if we were to start this graph here at 270, it would rise, reach a maximum, come down, reach a minimum, and then come back up. That's what sine is doing. So if you said, well, sine is just, cosine is just sine of x minus 90, that's correct. If I move this point over here, then you'd have a cosine curve. Imagine this is where we had the y-axis. You would have this curve here. They're the same. They're just horizontal translations. So we could use either sine or cosine in this case to model this rock that's been caught by the bike tire and is moving around the bike tire. And we know that these functions have period, they have amplitude, and they have phase shift, how much they're shifted side to side. They also have an equation of an axis. And those 4 elements correspond to our 4 transformations for functions, A, K, C, and D. So I'm going to go back there in a second to talk about that. How would having a bigger bike tire change the function that we graph for the height of this rock as it moves around? Suraj?
Period's longer.
The period might be longer, but then we might say the bike would then go faster. So the speed of the bike might be more directly affecting the period, but you're not wrong. If the bike was going at a constant speed, but the wheel was bigger, then yes, the period would be shorter. But what else is going to change more directly if we change the size of the bike tire? Amplitude, frequency, period, or equation of the axis?
The maximum value.
Yeah, the maximum value is going to be higher, right? If we had like a little bike tire like this, the pebble would come up and go down and come up and go down and come up and go down like that. But if we had a great big bike tire, it could come up and come down. The amplitude is going to be bigger. So the maximum is bigger, the amplitude is bigger. What about the axis?
Is that one of those old like 30s bikes?
Yeah, if you had like a little earlier in the 30s, I think you're thinking in the 1800s, but like those great big, I forget what they're called, where the
Yeah, like the huge one.
there's no gears, it's just you just pedal a giant wheel in the front. Yeah. So that one is going to have a very large amplitude. And in this case, the minimum value, like the rock is going to touch the ground all the time, right? It's always going to be the minimum value is going to go down to 0, not -1 in this case. So where's the axis for one of these situations? Dave? Yeah, here's your axis right there. It's the axle. It's actually where the wheel is turning, right? So that is the midpoint between the top of the wheel and the bottom of the wheel is going to be that mid horizontal axis. So if I had a bigger wheel, it's going to move that axis up. It's also going to move the highest point of my function and the lowest point of my function. Which transformation would control that? A, K, D, or C? Setting the size of the amplitude of my function. A. Yeah. A is going to stretch that. Which one would set the horizontal axis? Which one would set this point here? Okay.
See?
Yeah, it's going to be a vertical translation. So we want to translate the whole function up or down based on this axis here. If they did a wheelie and lifted the wheel up and the rock was turning like that, that would basically move the whole function upwards, but it wouldn't change the amplitude. It's still the same wheel. But that would be a higher horizontal axis because now the bottom point wouldn't be 0 anymore, wouldn't be touching the ground. It would be elevated in the air. And so you can think about all of these different changes. If the bike is going faster or slower, that's going to change what aspects of our function? If I take a look over here at my example, this one could also be modeling a bike tire as well. I should just leave it open. I feel like it's taking up a lot of computing power, but it's really not. If we take a look at this one, looks better over here. And I turn this on, this one here. So let's just pause that. So here is my, here's the bike tire. This is the ground, and this is the rock. Goes down, touches the ground, comes up, goes down, touches the ground, comes up. If I want to change the amplitude there, well, I just need to multiply this by, like, let's say 5, and that's a bigger bike tire. If I want to move it up or down, then I would just have to add something, like, let's say +2, something like that. So there is the bike tire. There, the bike is doing a wheelie. It's up in the air. If I say +1, there, that's the rock coming down, touching the ground every time. And this would be the height of the wheel. So the radius of the wheel would be the distance from the horizontal axis to either the maximum or the minimum. So these are all kinds of ideas that you can use to organize your thinking about these types of problems, these types of questions.
If the bike was doing a wheelie, wouldn't the tires slow down and that would change the function?
Yeah, and then you would have to model that by, you would want to have a progressive K. that stretched it out further as it went along, because k is going to determine the
So you're
period.
gonna have the k based on x.
Yeah, there's going to be some function that relates k to x, and so you end up with a very complex function to create something that's a faster sine wave in the beginning and a slower sine wave down there. And that's something you can play with in Desmos. So yeah, let's take a look at transformations of sinusoidal functions. We want to feel at the end of this lesson that we can take sine x or cos x and we can do transformations a, k, d, and c and transform this function in a variety of ways. We want to also be able to sketch the graphs of transformed sinusoidal functions. So we've graphed our parent functions in a quite detailed way using exact values from the unit circle. Now let's apply some transformation to these. So now it says, let's refer to our classmates' work to remember our transformations. So yesterday we... All right, so carrying on. So there are all of our transformations. Now let's take a look at our transformed sinusoidal functions. This is where you're going to see the transformations showing up in sine or cosine. And so if f of x is some number multiplied by sine of k multiplied by a bracket x minus d, we'll see. That's how they look. And that's how you would write them in Desmos, and that's how you're going to do your algebra on those things as well. So the a value, you want to get down here, what are the properties that the a value is going to change? Well, the a value is going to relate to maximum and minimum. And it's going to relate to, here you see the value, the function 2 multiplied by sine x. So it goes big here and then comes down and then goes small there and then comes up. I need a copy of the handouts too. And then you also see there 1/2 sine of x. And so that's this shorter one in there. So you see all of these different functions. It's also going to affect, what other values of the function is going to affect? Not just the maximum and minimum, but the amplitude. Yes, that's right, amplitude. So here's a larger amplitude. That's amplitude 2. This is amplitude 1, and this is amplitude 1/2. So what's the amplitude of g of x is equal to 15 sine x? What's the distance between the maximum of that function and its axis, or the minimum of that function and its axis? What's the distance? What's its amplitude? Julie?
15?
Yeah, 15. So the amplitude of g of x is equal to 15 sine x. It's 15. It's the a gives you the amplitude, because the amplitude of the base function is 1. So if I multiply those outputs, that's going to change the amplitude on a 1-to-1 basis. Keep going. What are we going to get from k? Let's take a look at k here. So the a value, so yeah, we have here the amplitude for each of the following. This is an amplitude 4, and then this is an amplitude 1/3. And so yeah, that's amplitude. But now let's take a look at k values. So if we start changing the k values, it's going to affect what aspect of the functions? Here you have, this one is going through, notice that the blue one goes through a full period in 360 degrees there, 360. So that one is cosine, just a normal cosine curve. This one here goes through a full period in 2 times cosine, and this one goes in a full period in, I got some funky numbers there. Weird. Oh yeah, no, this is better on the graph. So anyway, notice that the period is changing here. The k value is going to affect our period, and the formula that you can use, k is equal to 360 over the period. This is going to affect your functions. This is how you can change the period of your functions. So if the bike is going faster, that means the rock goes up and down quicker, and we need k to be larger. So you're going to divide 360 by how fast it's going to go up and down, and that's going to give you your period. So that's going to give you your k value. So if we take a look again, just down here, when I wanted this one here, I'll just put on the grid lines for you. And here's the axis numbers, the grid. So I wanted a full period in 1, so that it would go from 0 to 1, and it would also match here. I'll just get rid of this, because I wanted this to match the unit circle. So I wanted it to be as tall as the unit circle, but also be related horizontally as well, just so that you would see a full cycle of sine in the space of one grid line. So I have to multiply here by a k value of 360, because I want my period to be 1. So I have 360 divided by 1 is 360, and that's my k value. And it squeezes the function by a factor 360 towards the y-axis. This is what happens if I take that out. Notice that now I need to show you 360 degrees to show you it going through one full cycle, so you can hardly see any change there. But if I put that back in, there you go. That's one whole cycle in 1 unit on the x-axis. Let's keep looking. Let's keep going. So if we have questions like, what value of k do we need so that our period would be 60 seconds? How would you do that? If you wanted to create a function with a k value of the k value that would give you a 60-second period, say f of x equals sine of some value multiplied by x. What value do I need to put in there and multiply my x by to get a 60-second period? Sorry? So there I can use this function here, this formula, to find how to do that. I want it to go through one full trigonometric cycle in every 60 seconds. Say the bike is moving so slow that the wheel goes around once every minute. Yeah, really slow. Maybe they're doing a wheelie and it's just moving so slow. What do I put in for k? I want the period to be 60 seconds. So what value of k will do that? Well, it'll be 360 divided by 60. So what's that? So 6. Sine 6x. Okay, let's take a look at it, sine 6x. So I'm going to go over and create a new Desmos. We're going to look at this one. And because I can sense that we're not really following that idea, let's take a look at, we want to see x values up to and past there. We should see 2 full cycles here at 120. If I have, and I need to switch to radians. You'll also notice that Desmos is always set to radians. You want to flip it over to degrees every time for this course because we don't work in radians. So here I have y is equal to sine of 6x. And there I see I'm going through one full period every 60 seconds. See that? There's one full turn through my sine curve. There's the maximum at 1, and it happens at 15. And then here's the minimum at -1, and it happens at 45. Why is that? Well, 15 times 6 would be 90. And so that used to be sine 90 out there, but now we get that by sine 15 times 6, which is still 90. And that's why that transformation is doing that. That's why it squeezes it. If I don't have this 6 in here, you'll see it's much, much flatter. And there's that point 91. If I squeeze that 6 times towards the y-axis, that's the desired function that has a period of 60. You see it? Now, how did we do that? How are we going to do that algebra? Use this formula. So if I know this formula and I want to have a period that's 2 hours, something is going to maybe like a tidal rise and fall or a very slow Ferris wheel. How would we get this period of 2 hours? What value of k will do that? No, not 3. If I want 2 to be my period, I put this in here, so I would have 360 divided by 2. Dave? It depends on what your x is. So what is your x measuring? That's a good question. Here, when you're looking at a 60-second period, x is an input, and it's a number of seconds. If you have a 2-hour period, then I'm assuming that your x is a number of hours. But if it's not, if x is a number of minutes, we can still use this function. Let's say we wanted them to graph on the same axes, and we show one is a 60-second period and the other one is a 2-hour period. You would have to figure out how many seconds 2 hours is and divide 360 by that many seconds.
Isn't that answer 180?
Yes. So if we take a look over here, and now I graph sine of 180x. There. Notice that it goes through its period a lot faster. It's been squeezed a lot. So this, if I zoom in now and show you, here is 2 hours, you see? There's 2, and it's gone through one full cycle by then. There. It went up, reached its maximum, went down, reached its minimum, went up, and there's its full cycle, there. 2 hours. So you just use this formula, 360 divided by the period, and that will give you the appropriate value of k to match your sinusoidal function to the situation you want to describe. Okay, it's break time, go. All right, welcome back. So we know that the k value is going to determine the period of these functions, and one trick that you can use is, remember that the k value tells you how many cycles you'll see within 360 degrees. So if I want that to go up, go down, and then come back up again inside 1, then I need 360 as my k value to have a period of 1, and then I will see 360 cycles in 360 degrees, and 360 along the x-axis. So if we take a look at these types of problems, and I have a few different ones for you on the sheet, so the ones on your sheet are different. You can do those. If I have sine is 2x, and I want to know what the period is for that, well, I can find out by using this formula here. Period is equal to 360 divided by k. So in this case, the period is going to be equal to 360 divided by 2. Well, that's 180. That's a question that I asked you just a second ago. So the period there would be 180 degrees, or 180 of your x. That could be 180 seconds, because we might be looking at a Ferris wheel where x changes with time. And so my input is time. It's not an angle. And so that would be 180. Here, cosine is 1/2 x. Well, again, I just take period, and I look at 360 divided by 1/2 is the same thing as 2 times 360 is equal to 720. Also, this number here, k, 1/2, tells me I will see 1/2 of a cycle within 360 degrees. So I will see a full cycle in 720 degrees, so my period is 720. Now on your sheet I said, what's the period of sine 12x? So who can tell me, what's the period of sine 12x? So if I have this question here, sine of 12 times x, and I want to know how many degrees is that going to take? What value of x is going to bring that through one full cycle? What will it be? Suraj?
30.
Yeah, 30. Yeah. So we look at this and we say, if that were to equal 360, that would be one full period. So if, and that's where this formula comes from, right? Period is equal to 360 over k. So here, I would say the period is equal to 360 divided by 12, and Suraj just told us that that's 30. Okay, so let's take a look at it in Desmos. I want you to see these things and be able to visualize. You want to be able to visualize these things. Here, if we take a look at 12x, so there, if we look out at 30, there's 30 there, and that's one full period. So it rises to its maximum 1, goes down, and then hits its, finishes the period there at 30. So that's sine of 12x. So Suraj is correct. And then I also asked you about g sine x is 1/2 sine x over 5. What's the period there? If we have another one where g of x is a function that's equal to 1/2 multiplied by sine of x over 5. What's the period of this function? First, sorry? So does this 1/2 affect the period? What does that affect? Yeah, the amplitude. So that's an A transformation. Here's our K transformation. Our K transformation is divide by 5. So that's going to be a horizontal stretch of factor 5. Sraj?
1,800.
Yeah, 1,800. So here we use this formula here to find it out. 360 divided by 1 over 5 is 360 times 5, which is 1,800. Great. So this has a period of 1,800. And we got that from solving this equation. P is equal to 360 divided by 1 over 5. Gives us this. Okay, so that's all you do. You just apply these formulas and develop your intuition by looking at graphs and thinking about when I stretch these functions this way, that way, move them up and down, shift them left and right, what's going to happen? It's a very visual unit for me. The D value, that's going to affect, what are some of the properties that it's going to affect? Will it affect, for example, the maximum and minimum? No. Will it affect the intercepts, the y-intercept, the x-intercept? Yeah. The D value is going to shift the function left or right. So if I want to shift these functions left or right, let's take a look at them. Here is a sine of 12x. And if I want to shift that, we usually write these D transformations, like this, inside a bracket. And if I want to go like, let's say, 15 that way, so that's shifted the function 15 in one direction, 15 units. If I go 5 here, or 1, you'll see it shifts around 5 and things. And if we take a look here, let's put in a slider, x minus d, and I'll add a slider there. And now we'll see as this moves around, we're just shifting the function left or right. So there, if I wanted to shift this to make it equal to cosine, looks like I need negative 7.5 there. That's actually x plus 7.5. I like thinking about it that way better. If I go x plus 7.5 up here, you'll see that makes it equal to a cosine curve, and cosine and sine are just horizontal translations of one another. And so you can actually get into Desmos and play with the sliders to find the answers to these types of questions, if you like. And that's a good way to develop your intuition for these things. These are useful if, like, you get on a Ferris wheel, but you don't get on at 0 degrees. Usually we'll get on at the bottom of a Ferris wheel. So if I want this to model that, I want this to be my y-intercept, I could just drag this around until I get, okay, there we go, negative 7.5. And that will do it here. Why is that happening at negative 7.5? If I do the algebra here and I multiply this in, I would have 12x plus 12 times negative 7.5. 12 times negative 7.5 is negative 90, right? So that will do it. That would be sine with a translation rightwards of 90 degrees. Let's keep going. So state the phase shift in y-intercept. So let's find our y-intercepts for these two. What did I give you to do? I'll leave those for you as kind of homework questions for the D. The 15 sine x minus 30 and the cosine 12x plus 10. So here, if we said sine x plus 45, let's go ahead and take a look at our vanilla sine graph. So I'll get this to just be vanilla sine here, and we'll have dB0 to start. And I'm going to change the scale so I can see all of the full period. So I have to change the scale here. And changing the scale, that's the same thing as doing a K transformation to your picture. It's kind of a useful thing to remember. 360. So there is one full cycle of sine. And if we wanted sine of, what did we have here? X minus 30, is that the one we have here? Sine x plus 45. So if I add plus 45, let's visualize what's going to happen and check. Plus 45, that should move the whole function to the left because it's a weird sign flipper, so it moves in the negative x direction by 45 degrees. So that would take this point here that happens at 45 degrees and make it the y-intercept. So that's going to be the new y-intercept there. It's 1 over root 2. 1 over root 2 will be the new y-intercept. Let's put it in there. There's 45. There. 1 over root 2. So it shifted it this way by 45 degrees. That's what happens. What's our other example that we want to look at? Cos of x minus 30. Okay, so now I'm visualizing. I want you to be able to do this in your head. Cosine looks like this. There's my y-axis. If I shift it positive 30 degrees, it's going to be root 3 over 2, and it's going to be rising. It's going to be that first point, that negative 30 degrees is going to be the new y-axis. So that's going to be at 0.866. Let's try that. So first I put in cosine here, and I'm going to want just cosine. So there's my point. I predict that this point here at negative 30, where's negative 30? There it is, negative 30. That's going to be the new y-intercept if I say cos x minus 30. There it is. So it's a horizontal translation, and it changes where the function starts. It changes its initial value. It also changes all of the intercepts, so the places where it meets its own axis, they're also going to shift along because the whole shape changes with d. And now let's carry on. The c value. The c value changes the axis. It changes the axis. So write that onto your page. But it also changes the maximum and the minimum. Changes the maximum and min values. It changes the y-intercept. It changes all those things by lifting it up or down. That's the bike is going along the ground, and then they do a wheelie. So now the rock is moving around in the air instead of touching the ground every time it goes through one period. And so if we look at something like sine x plus 2, that's vertical shift up 2, and the equation of the axis is y equals 2 here. For f of x, sine x is equal to plus 2, so that's y equals 2 is our equation of the axis. Here, cos x minus 3, the equation of the axis is y is equal to minus 3. The examples that I gave you, what is the horizontal axis of 15 multiplied by cosine of 12 times x plus 10? All plus 5. It's a very complex trigonometric function. It has all 4 transformations applied, but only one of those transformations will influence the horizontal axis. What's the equation of the horizontal axis of this one on your sheet there?
Y equals 5?
Just y equals 5, yeah. It's just that C transformation. So C transformations change the axis. D transformations shift the phase. It's called a phase shift. And for those guitar players out there or people who are interested in audio, shifting the phase of a sound signal can create some very interesting warbly effects. A lot of your favorite music uses what's called a phase shift, which sounds really cool. I'll play you some examples later. Already this is pretty long. So domain and range. These transformations affect the domain and range. The domain's never affected because there's always an output value for every input value. So the domain is always x's of the reals. But the range is always affected by A and C. If we increase the magnitude, it's going to increase the spread of the range. And if we change the C value, it shifts the whole range up or down. And blah, 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 blah. Okay, so that we've done already. And now it's time to say, get yourself moving. So, yeah. All right, so let's see. I have here for you on the second page of your handout the practice problems for today. And so the practice problems that we have are listed here. Day 2 practice problems, page 309, 1 to 9 are useful. 11A is good to take a look at, and 318, 1 to 2. But one thing that I want to do before we do that is to go over this example here, where we're going to try to find a trigonometric function that will match what we're seeing here. So let's see how we will do that. The first thing that I would do, looking at something like this, is identify what's the equation of my axis, what's the amplitude, and what is the period of this function. So looking at this example, what's the period of this function? Suraj?
4.
Yeah, the period is 4. So I'm going to have that in there. Just write in a 4 for yourself. Wait, I have this on this one. I have this ready. Yeah. So we have here the period is 4, and Siraj measures that by taking a look here and saying, how did you do that, Siraj? Did you use this point?
I use the bottom.
So use the bottom here. So he looked at this point, it's at 2, and then this point at 6, and to find the period, he just measured this distance there. So the period is 4 long. That takes it through one cycle. Notice that we could also use this point here, and we could say, well, it's at the midpoint, it's going down, it comes up, and then it goes down again and reaches 2. So that would be one full cycle as well, but that would also be 4. It's 1 to 5. Doesn't matter where you take, but I can't do from here to here. That's not a period because that's not a full cycle. Not only the point and its height, but whether it's rising or falling matters. So we have the period is 4. So we need a k value, and we can use this formula. K is equal to 360 divided by the period, 4. So we want a k value here of 90. There. So that's our k value. We've determined that. Now, if we were going to do a, take a look at the axis, what's the axis here? How do you find the axis of this function? Dave?
I go to the middle of the amplitude.
Yeah, so right in the middle, and we can kind of visually see that it's there. But let's use some algebra and prove that it's at y equals 2. So that's the midpoint of this midline of this function along here. And we do it by taking the maximum and the minimum values and averaging them. So the maximum value is 5. The minimum value is -1. If I take 5 and add it to -1, I get 4. But I'm doing an average, so I divide by 2, so I get 2. There we go. There it is, right there, 2. Yeah. So we know that one of the transformations should be equal to 2. So the equation of the axis, y equals 2. So that gives us c is equal to 2 here. That's another one of our transformations we're going to apply. Now, what's the amplitude of this function? How much is the maximum elevated over the axis? How much is the minimum underneath the axis? Is what that question is. Suraj? It is 3. So we do that by subtracting these two and then dividing by 2. It's the distance between these two. So 5 minus -1 gives us 6. That's basically saying what's the distance between the maximum and the minimum. And then I divide by 2 to get the amplitude. So the amplitude here is 3. And we can see it because 5 is 3 above 2 and -1 is 3 below 2. So the amplitude equals 3. So what transformation will have a value 3? A, K, C, or D? I want to stretch everything vertically by factor 3. So what am I going to do transformation-wise? Sorry?
I don't know. I don't want to say because what if I'm wrong?
Would it be stretch or no?
Yeah, it's stretch. Yeah. So which one is that? A or K? A, yeah. So it's a vertical stretch. Amplitude is A. It's just kind of easier to remember if you see, amplitude, A. Okay, I got it. So A is going to be equal to 3. All right. And then the last thing is phase shift. How much do I need to shift this side to side? And it asked us to create sine and cosine both. We want to create both a sine and a cosine for this function. So let's do cosine first. Has this been shifted if we're using cosine? No. So if we're using cosine, then d is just going to be 0. Okay, so let's just do that. So we're going to have f of x is equal to our vertical stretch, 3 times cosine of our k value, 90, multiplied by x, and then we're going to add c. You're going to add c plus 2. So now let's go ahead and we'll graph that in Desmos and see if we're right. That's just putting together all of our transformations. So here's a Desmos. I'll actually use a fresh Desmos for this. because I don't want to show, I just want to see that it, it works in these numbers here. Now let's put it in. 3 cosine of 90x, oops, 90x, is that what we said? Plus, oh yes, I'm still in radians. Ha ha ha. I had that like, oh, I'm making a mistake in front of everyone type of feeling. That feeling that Brody was worried about. There, is that the function that we had before? Looks pretty much exactly like that function, right? It starts at 5. It goes down to the point 2, -1. It goes up to 4, 5 there. Let's check our original function. Yeah, there it is, 4, 5. There's 2, -1. Yeah, that's that function. So that's how you do it. Oh, that's how you arrived just for the that's how you do it part. Hey, Liam, that's how you do it. Yeah, I've been talking like nonstop the whole time, and now you get to that's how you do it. Okay, so if we wanted to do this with a sine wave, what would we need to do to make a sine wave work? Give you some hints. It'll have the same A value transformation, the same K value transformation, and the same C value, but it has to have a D. Yeah?
We have to have a D of 1, so that would translate to the sine.
Yeah. Yeah, it's going to be a D of +1. That'll do it. So if we have
Positive or negative, right?
sorry,
Positive or negative?
no, because it'd be the different directions. It would be rising instead of falling. If you had +1, I think it's +1 that we want because we want it to pull this way towards the negative by 1. So we look at this. Here's the point. This would be the y-intercept if this were sine, right? It would go up. So I want to pull it that way by 1. So we put in a transformation of 1. Great job. 3 sine 90 multiplied by bracket x plus 1 plus 2. Let's test it and see if it's the same as this other function that we had here.
Isn't it minus 1?
I think it's plus.
All right, let's see.
Let's see. 3 sine, and I'm willing to be wrong here and not check my work here. This one plus 2. There it is. It's +1. So notice that if I just use a slider there for D, and I'm going to add a slider, okay, and we're going to go down to 0 here. This is my sine curve without any horizontal translation. There at D is 0. And I want to take this point here and move it in the negative direction 1. So I put that inside the bracket there. I'm going to move this by adding 1 to it, actually shifts it in the negative direction. And it's a weird sign flipper, so we want to make sure that we remember this one is counterintuitive. And so there it goes, and it hits that curve that's our desired curve. So that's the value of sine. That's the sine function, sorry, that would match that curve that we wanted to create. All right, so your practice are these types of problems here, these day 2 problems. And I'm going to spend the rest of the period moving around and chatting about these ideas with you. If the people who are at Shazam want to take 10 minutes and go over it in the Reader's Digest version, maybe we can all congregate here and I'll show you on the overhead. Otherwise, get at them, everyone, and try some of these problems. See if you can create some of these functions.
Yeah, can we go over?